We are talking about mixed designs, and I have begun with a review of between subjects factors. In this video, I want to review within subjects factors. The difference of a within subjects factor from a between subjects factor is that while in a between subjects factor, each unit is measured at only one level of the factor, for a within subjects factor, each unit is measured at all levels of the factor. Referring again to a study that we looked at in a previous video series, I looked at soccer players' sprint times with repeated trials. So when we look at these box plots, unlike with between subjects factor, each box plot is made up of participants in the study, and in fact, each box plot is made up of all participants in the study. So the first box plot is all participants at trial 1. The second box plot is the times of all participants at trial 2, and so forth, all the way to trial 6. So each unit is measured at all levels of the factor. The effects that we estimate are estimated after removing the variance due to the units. That is, we're eliminating between subject variation because that's not what we're focusing on. Instead, what we're focusing on is the within subject variance across the levels of the factor compared to the within subject variance that is unassociated with the levels of the factor. So descriptively, we can again compare means for each of the trial times. But if we want to compare those means from each level of a factor to the other levels of the factor, we can see the medians here in the box plots and the means in our descriptive statistics. If we want to compare them in terms of the relativeness to the within subject variability, which is always important to do because means can vary just due to sampling variation. We want to know, is what we see in the mean differences due to sampling variation, is that just a function of that sampling variation, or is it something more than that? We can go down to our analysis of variance table here and note that what we did is we took out the variation that was due to between units. You can see here in this term it says ID, and ID was for every single soccer player. And so therefore what we're removing from the ANOVA table that we're going to focus on, the one down here, what we're removing is the variation between those soccer players before we ever get started in looking at the variation due to the different trials right here, and then the variation that is also within the subject variation, but this time going beyond what we see to being in the different trials. That within subject variation that is not accounted for by the different trial is our residual that we're using. And so what we're wanting to do is to compare the variation between trials and that variation, comparing it to the residual variation. In this case, one of them is 9, almost 10 times the other. And therefore, it seems like trials do make a difference above and beyond the fact that we have variation that we cannot account for simply by what trial the soccer players are in. In order to be able to go over here and look at that p-value and know that it means something, we have to consider the assumptions for valid inference. The first assumption is independence of units within a factor. So if I go back and look at those box plots again, what I'm saying there is that all of the units that make up this first box plot have to be independent of one another. They're not going to be independent across levels of the factor because the same units are going to appear in trial 2 that appear in trial 1. But the units have to be independent of one another within each of those trials. Then we need sphericity. This is like our homogeneity of variance assumption. Indeed, it is a homogeneity of variance assumption, except it's a homogeneity of variance of all paired differences. So remember when we did this analysis that we actually created difference scores. Let me go actually to my notebook here so we can find that. Here it is. We actually created all the possible differences for each individual. We looked at the difference between trial 1 and 2, 1 and 3. We calculated all those differences for all the individuals. In this case, there were 15 of them. And then we looked at all the possible pairs to see what kind of variation we got across all the possible pairs. And what we ended up with in this case was something in which the variation looks very similar from one pair to another. And if the variance is equal in the population, we're not looking at populations here, we're just looking at the few soccer players that were in the study. But if based upon this data, it seems reasonable to believe the variation is similar in the population, then we have what is called sphericity, homogeneity of variance of the paired differences. The residuals must follow a normal distribution. We've seen that before, even when we had between subjects. So here we again created a QQ plot. And in this particular case, there's a little bit of deviation here in the center from the line, but for the most part, that looks like a fairly normal distribution. And so in this case, what we determined was that we could make valid inferences, and we were able to go on to our p-statistic for the omnibus test, and we were able to set a confidence level that we could believe in for the individual contrast test, in which we looked at differences between pairs of trials. Examples of within subjects designs are the repeated measures design, and that's what we have here. We have a repeated measures design. If you look at these box plots, these are the same individuals being measured 6 different times. That's repeated measures. But another design that we could have is a randomized block design, and statistically, this is analyzed the exact same way. In a randomized block design, what we do is we match individuals. So if I was going to use the same soccer study with 6 different trials, but I didn't want to use the same soccer player for each trial, which wouldn't make a lot of sense because the whole reason for that study was to see if they got better with practice or if fatigue set in. But if I was doing some sort of study in which I could potentially match individuals on an extraneous variable that was related to the response variable. Extraneous variables aren't actually extraneous variables if they're not related to the response variable. If I match on variables related to the response variable, then assign 2 conditions after matching, then I would have a randomized blocks design. Randomized blocks designs are very powerful, as are repeated measures designs, and the reason they're used because sometimes we can't use repeated measures designs because of multiple treatment interference. That is, if you're going to measure people repeatedly, and when you're measuring them, the different conditions are based upon what happened in previous conditions, such as if you were to have multiple instructional methods and how someone learns in the second method could be interfered with by how they learned in the first method, then you have multiple treatment interference and you don't actually get a good evaluation of the effect of each of the individual treatments. That's a good time to have a randomized blocks design. So the between subjects factors, everyone is at only one level of the factor. The within subjects factor, everyone is at each level of the factor. And so now we're going to put both of those into a single design, and that will be a mixed design. So I'll introduce that in the next video.